And on behalf of the team, I'd like to welcome you to this first out of 7 webinar events that we're hosting this winter. So just a little bit of background on MERIDIAN. MERIDIAN is a 3-year project funded by the Canada Foundation of Innovation. And I'll bring up the funders and the partners here. We also receive support from the member universities, and that includes Dalhousie, Université de Québec, SFU, UBC, and University of Victoria. And we also have several industry partners, notably JASCO and Exact Earth. This webinar series in particular is funded by a grant from DFO under the Ocean and Freshwater Science Contribution Program. And then finally, I'd also like to thank Pisces Research Project Management, Daniel, Kieran, Kes, and the rest of the team for their help with preparing and running this webinar series.
Oh. It's probably down in the kitchen. I just fucking, oh, there it is. I just fucking repatriated it.
No.
Which one do you want?
Whatever.
Probably go with this one.
Daniel, do you have an option to mute?
Yeah. Yeah, I just didn't know exactly where it was coming from. Sorry.
Me neither. Anyway, I'll proceed with the rest of the welcome here. So at MERIDIAN, our mandate the last few years has been to support the ocean research community through the creation of software tools for managing, analyzing, and visualizing underwater acoustics data. And so as part of this webinar series, we will be showcasing some of the tools that we have created in the last couple of years. Today's webinar will focus on modeling and visualization of underwater soundscapes. And so we'll hear about the Ocean Soundscape Atlas, which is an app that the MERIDIAN team in Rimouski, Quebec has developed. And we'll hear about the challenges of managing vessel tracking data, AIS data. And then finally, you'll hear from me about a new Python software package for modeling ocean ambient noise that we're working on. So let me bring up the program for today. So we have 4 presentations planned, and each presentation will be about 20 minutes, followed by some time for discussions, questions and answers. We'll have a break halfway through, a short break, and then we'll have the last 2 presentations after the break. So I think we will just jump to the first presentation at this point, which will be given by jointly by Pierre and Édouard from the Rimouski MERIDIAN team. And they will introduce the Ocean Soundscape Atlas and tell us a little bit about how the noise and risk maps have been created. And so we're going to have questions at the end of the presentation, but feel free to type in questions as they pop up in your mind throughout the presentation in the chat, but we'll take those at the end after the presentation. So I'm going to stop sharing my screen now, and then Pierre and Édouard, you will have to share your presentation from your own computers.
Pierre, you are at the mic.
Yeah. So, do you see my screen?
Yes, we see. That's okay.
Okay, perfect. So, like Oliver said, we will talk about the Ocean Soundscape Atlas. I'm Mercure-Boissonault, and Édouard Philippe will also help me talking to you about what is the Soundscape Atlas and what kind of map we found in the Soundscape Atlas and how we produce them. So to give you a bit of context, we see a trend that there is more and more ships over the years in the Canadian waters, and we fear that it may impact negatively endangered marine species because they produce a lot of underwater noise. For instance, the species that might be affected by the shipping noise are the North Atlantic great whale, the St. Lawrence beluga, and the killer whale in the west coast. So the researchers
Pierre,
models.
Can I just jump in for a second? Would you be able to come a little closer to the microphone? The sound is not coming through so clearly. Thank you.
Okay, so so researchers are doing some validation of acoustic maps to verify that. But wherever those datasets they generate are really huge and are highly dimensional, which make it difficult to share to other collaborators. And also, they cannot really be put on typical web platform like SSG. Usually, those platforms doesn't take into account the frequency or the time that we usually get in the acoustical world. So we came up with the idea to make our own web application for the underwater acoustic data. So this application will allow the user to browse, visualize, and analyze underwater acoustic data in all the dimensions that the data offers. And it will allow to assess the effect of the noise on various species and raise the general level of knowledge about underwater acoustics. So we are targeting mainly scientists there, such as oceanographers and biologists, and also we that may be interested in the effect of the noise on various species to, for instance, pass labs to change shipping routes, for instance, stuff like that. And also for it will be available for the general public freely on the web. Also, the Soundscape Atlas is a bit an effort to help the scientists improve their data production, data management, help them with the quality control and data diffusion. So when we talk about the Soundscape, the Soundscape contains all the possible sounds that you can find in the environment. The first category of sound that we have here is anthropophonic sounds, which are human-made. So in that category, we have mainly shipping noise, but there is also other sources that can produce noise, like offshore oil platform or geophysical surveys. Secondly, we have the Geophony noise, or sound maybe, so excuse me. So in that category, you have mainly weather-related sounds, like wind waves, rain and sea ice that can produce sounds just into the environment without not just naturally. Finally, we have biophonic sounds, which are made by marine species. In that category, we can include communication calls from the North Atlantic right whale or concussion sounds from the beluga or the killer whale. And there's a bunch of other sounds that some fish and other marine species do in the water. In the current case for the Soundscape Atlas, we are mainly interested in shipping noise and for the Geophony sounds from the wind and waves. The Geophony will give a bit of reference to the shipping noise to see how much the shipping noise is much higher than the Geophony. So I will talk to you a bit how we produce the shipping noise datasets. So we have to start, of course, from the acoustic model. So what an acoustic model does is it produces a transmission loss map, usually over a vertical slice. So it returns usually transmission loss data. So for those who don't know, transmission loss is a bit an indication of how much the intensity of the sound have reduced because of the, let's say, the sound absorption or the sound attenuation, or if there are interference between the two sound waves, for instance. Using that information, we can compute the level at each receptor of the map using the simple formula, which is the receptor level will be equal to the source level minus the transmission loss, all in decibel. I didn't talk about the input here, but I can say that we usually need a bathymetry profile, some water column properties like the sound speed or the sound absorption or density that usually change over the depth in the water column. Also, there is bottom properties that we can send to the model, and a bunch of model parameters like the frequency or the source depth. There is a wide variety of acoustical model. I won't go in detail into each model type, but I can say that there is each model type has its own strengths and weakness. For instance, in our case, we use a parabolic equation model at low frequencies and a ray model and high frequencies, so that we can do a good job in shallow waters. Yeah. The next step I will talk here is about Ramdam. Ramdam is a MATLAB code that was developed by Florian Lenny, DFU. And what it does, it automates a bit all the process surrounding the model. So it prepares all the input files that the model requires and receive and convert the outputs from the model. So first of all, we have to send Ramdam, give Ramdam a bathymetry map, a temperature and salinity map that would be later converted to water column profiles, and also bottom map of the bottom properties. Also, we are using AES data to know the position of the ships, and we use also the length of the ship and the speed of the ship to estimate what is the sound that each ship produces with a model of the sound levels that was made by Inasmar. So what Ramdam does with all those inputs, it prepares a bunch of vertical slices, and it interpolates the initial input into interpolate, let's say, bathymetry profile or interpolated water column profiles. What you get from running those models is that you get a bunch of vertical slices around each source, which can later be interpolated into a 3D map. And if you add the contribution from each source, you have a general timestep map of for a specific time of the year, using for the shipping noise levels. Using spatial map, you can also do probabilistic maps, which are a bit of a statistic about the sound pressure level maps. And from the probabilistic map, you can do impact risk map, for instance, to know how the sound will affect a certain well, for instance, and for certain consequences, stuff like that. Édouard will talk to you more about later. Also, we can do validation from the probabilistic map and compare that model data to hydrophone data to make sure that the two correspond. And so we can, if they don't, we can adjust the modeling code to make sure that it would correspond in the future. So to give you an idea of what is a sound pressure level map, there is a figure for it here. So yeah, you see clearly that there is a sound average H sources, and that is more intense near the H source or ships in this case. So to produce a statistical map or a probabilistic map, what we do here is that we are looking for H point. What is the variability of that point over a span of time? I figure here that show, for instance, of the sound pressure level values over a span of 1 month. So we can see there that there's also variability and sometimes some spikes that are happening during the month. So what we want to do here is that we want to know the distribution of those points. We do that by computing a quotient around each point in relation to their uncertainty, and we add all those the contribution of all the Gaussian together. So it produces a probability density function. And from most of you will know that from a probability density function or a PDF, we can use the area under the curve to know what is the probability of being above or under a certain threshold. So for instance, here, if we are then set by the value of 95 dBs, we'll know that there's 20% chance of being above that value and 80% chance of being below that value. Usually what we do in our case is that we, instead of saving the probability density function, we save instead the integral of it. So it's called the CDF or the cumulative distribution function. However, that curve is the probability of being under a certain threshold. And what we are more interested in the case is the opposite, is the probability of being above a threshold. So we call it the risk of exceedance, or simply risk, which is just 1 minus the CDF. And also, using the CDF, you can also compute the quantiles easily, since the quantiles are actually the inverse function of the CDF. So let's say that we want to know the ATF centile, yes. We just have to find where that line crosses the CDF. And for instance, we can find quickly that it's equal to 95 decibels. So this is an example. We can clearly see that it will be useful for analysis. For instance, we have we can see that the shipping noise is really focused around the shipping noise, and that also the battery sweep is very applicable here, since the sound is much higher near the Laurentien channel. That is much deeper in the middle of the St. Lawrence Gulf. Also, I will talk a bit about the issues we have with the files, the database size. So let's take, for instance, one map and 21 depth, so it would be like a 2D space. From that, we have to add another axis for the time. Let's say that we have want to make probabilistic map for 365 days. Over that, we have to add another axis for the frequency. We have in our case 11 frequencies, and once again we have to add another axis for the risk and quantile to talk about the distribution of about its distribution. So it make about 15 million maps, which is, yeah, it's quite a number, and it makes about 30 terabytes, and this is just for one source type and 1 year and 1 region. So if you want to have, for instance, we want also to have the same thing for the Geophony, for instance, or if you want to have extra layers, or if you want to do for the computation for the regions, it will be a factor of that of those sizes. So I will let Édouard continue with the Geophony. So Édouard,
yeah. Yes, thank you, Pierre. Me, I will present you the Geophony. Pierre present to you the Geophony. It's the sound from wind, waves, rain, sea ice, or earthquake. But we make a simple Geophony, just with wind and wave generated by wind. For this, we have access for the wind velocities. You can see the variation of the wind during the January. And we use the wind function to compute the wind noise. And with this wind noise, we can compute with Kide square distribution. We compute directly the Geophony risk, or PDF and Quantile. For the moment, we have presented to you to compute the risk and the risk of Geophony or anthropophony. The risk is a useful metric for scientists, but we need to transfer this metric in other metric, the impact risk It is more simple for every people or decisional people to understand what's the impact directly of the chipping noise on different parameters of the geophony, or the impact or masking the geophony or other. So if you want more detail about the computing of the impact risk, you can see, you can go to read the paper of Olanier and collaborator in 2017. In the project, we have compute 4 impact risk: the behavioral disturbance, the state noise masking corresponding to masking the geophony, the reduction of detection or communication range, and the temporary hearing loss. To compute the behavioral disturbance, we need to use the risk that computed before by Pierre and the PDF of the behavioral disturbance. For this case, we find the behavioral disturbance PDF in the literature from Gomez and collaborator in 2016. And we can conclude directly the impact risk. And the impact risk for this period is more understanding for people than the risk, because you can understand the real impact of the chipping noise on the wave for the behavioral disturbance. And if you add the geophony, you add the anthropophony, you add the impact risk, you have really a lot of maps. It is really a big data system. But it's perfect for scientists because you have a big resolution, nice resolution, everything. But if you need to share this data, you need to think you share on website, you need to reduce this grid. For this, we create a second database. We name this database web database. And for this, the first step, we reduce the size of the grid by 6. For presentation, imagine your initial grid is 9 by 8. We reduce the grid to 3 by 4. For this, we reduce the size of the file by 6. But we continue. The data is stored in netcdf file. The float in scientific, it is double. It's 64 bytes, you have a great resolution. But for web, it's acceptable if we reduce this to single. It's a division by 2. After, in scientific, we have 20 layers for the depth. We reduce to 10 layers, more 10 layers interesting for the web. And we continue. For the risk of accidents, we have 531 level of SPL reduced to 13 SPL. For quantile, we make the same. We reduce to 101 percentile to 13 percentile. And if we take just anthropophony risk, just for daily, monthly, and annually file for 1 year, one region, we pass to 30 terabyte to 50 gigabyte. It's a big reduction, or compression, but we need to share this data in web file. And to conclude or summary this presentation, we have different inputs. We have the wind velocity, we have navigation, bathymetry, everything. With this input in the project, we compute directly the geophony or anthropophony in scientific grid. This represents a lot of map. With geophony and anthropophony, and we add other geophony PDF parameter, we can compute the impact risk in scientific grid. And after we have this scientific database, we convert this database in web database to share this new map to Patrice, who will present to you the result on the website. Thank you for your attention. And look the presentation with Patrice after.
Thanks, Édouard. Thanks, Pierre, for this nice introduction of the Ocean Soundscape Atlas. As you heard from Édouard, in a moment, Patrice will give you a bit more of a demonstration of the app itself. But we have time now for a few questions, if there are any, to Pierre and Édouard. You can, I think everyone here has the option to unmute themselves and just ask the question, or you can, if you prefer, you can also write in the chat, and I'll keep an eye on the chat, and then I can forward any questions from the chat to Pierre and Édouard. it looks as if there may not be any questions from the audience. I have just one little question for you, Pierre, before we move on to Patrice's presentation. I was just wondering if you could elaborate a little bit on the validation step that you mentioned. So, because this is an important step to go in and check that your model results are in reasonable agreement with the measured sound pressure levels. And I don't know if you could say a little bit more about how, if there is a discrepancy, how is that sort of, how does that feedback loop work in terms of what do you modify in your model to improve the agreement with the measured sound pressure levels?
Yeah, actually we didn't. It's a step that Ariane did earlier before I came into the MERIDIAN team. But I believe that it's to adjust mainly to to add a bit of a value of decibels over the source pressure level map, just to make sure that it will correspond. Yeah, but I don't really know actually.
Okay, yeah, I guess Florian would be the person to talk to about what was done there. Yeah. Okay, thank you.
Actually, I think Florian is present. But
normally
might not be completely present.
Okay. And, yeah, go ahead, Florian. Yeah, will you be able to elaborate on or provide some thoughts on the validation?
So the first step is to for the validation is to make sure that the model data just fit with the measurement. So the first thing you need to do is to make sure that your measurements are correct, and you need to clean them up, and you need to be able to separate as well, or to make sure that the level that you're measuring correspond or are dominated by shipping noise. So this is the first step that you need to do. And then once you have seen what is the uncertainty that you have, then you can include it in the model directly by fitting the. Actually, we do include the error distribution in the model. In the model. So this is a step that Pierre didn't emphasize, but when you put when you do the modeling, then you introduce at some point the uncertainty on the inside the modeling with a convolution. So there is a paper for that. That is Gervais et al. 2015 that is explaining this. So basically, the maps are called that you see at the end is not only it's a probabilistic map. It's not only statistics on the sound field, but as well it includes the uncertainty. So it's a Bayesian output, and so this is the first step. And the second one is to make a Bayesian inversion of under our acoustic parameters. And this has been done. For example, you have an example in Simard et al. 2016, where the model, I mean, to be able to estimate the source levels, has been tuned to make sure that you have the maximum not sure which one it was, if it was maximum likelihood or maximum a posteriori in kind of inversion, but you're sure that you have the best parameters that allow to model the sound field. So there are the two biggest steps. Still, at the moment, it's not. I mean, the work to include it in the pipeline, like as a production pipeline. I'm talking about the second step, the Bayesian inversion. Is not like fully included. It has been done on several cases, but it needs to be worked. So it is work going on, research work going on. So I don't know if it does it explain it a little bit.
Yeah, absolutely. Yeah, that was very
Okay.
helpful. Yeah, thanks
Okay.
for jumping in and providing such a comprehensive answer. Thanks.
You're welcome. Thank you, Oliver.
Okay, perfect. I think we'll just, it's time now to move on to the second presentation by Patrice. And just, yeah, but very briefly before you start, Patrice, I just want to, again, I was just looking at the number of participants. And I'm quite impressed at the number we've got here, more than 30. So I just take the opportunity to thank everyone again for joining here. Yeah, so Patrice, feel free to share the screen at any point now. And
sure, thank you. Before that, can you just make sure that when I speak directly in the screen, it sounds okay?
Right now it sounds good. Yeah, so right. I'll let you know if yeah.
Thanks. So let's go ahead. Thanks, Oliver. All right, Soundscape Atlas. So what is Soundscape Atlas? Soundscape Atlas is a state-of-the-art web application dedicated to explore georeference dataset with additional dimensions. The primary purpose is to explore acoustic environmental impacts in specific bodies of water. Secondary purpose is to develop an infrastructure able to host most of the multi-dimensional georeference datasets existing in marine science, like geological surveys, ocean atmosphere conditions, remote sensing, etc. Now, a more practical answer would be that Soundscape Atlas is the first web platform of its kind to put the knowledge and big data exploration capabilities of marine acoustic experts at the disposition of scientists, students, decision makers, and all those interested in the impact of noise on the marine environment. Who made it happen? Well, it's actually a collaborative effort between the MPO EML, UCAR-ISMER, Dalhousie University, OGSL CUs, which span a vast variety of expertise and disciplines, and also span almost 3 years of work, dedicated work to make it happen. But how does it work? Well, actually, Soundscape Atlas is 2 applications. The first one is the part where we transform the scientific data into a more manageable dataset, which we put in our database under 2 types of representation. One is for our GeoServer, and the other is for more specific operations. Under contour point clouds, and the other is under rasters representation. So actually, as an order of, I would say, magnitude, we transform about 500 terabytes into 3 terabytes to consume in the user-facing application. So here's the user-facing application with 3 services. One is to service the actual maps, which we'll see soon. And then there's the server for who distributes the actual application. And then we have an API which allows us to explore with more fine-grained utilities. So let's go ahead. Can I see a platform action? Sure, follow me. So this is Soundscape Atlas. First, we have a disclaimer just to tell you that the actual data is is available, but has not necessarily been peer-reviewed by all people, and we use actual open government license. So once it's been read, we'll start and we'll see and start the tour guide. So first, to become familiar with the platform, we'll answer the following question. So which zone of the St. Lawrence estuary and Gulf has a shipping noise risk that will unlikely reduce the communication range of blue whales by half? So we'll use the application to answer this question. And the actual answer is right there, but we'll roll back and see how to get there. So the first step would be to translate the question to the actual meaning within the application. The parameters would be the scent length estuary Gulf in 2013, where the risk impact on the reduction of the detection communication run is under 33% of probability for 20 Hertz at 100 meter depth. So next, to select the actual map, we'll use this utilities, but first let's see all the utilities available. So we have, we can extract statistic on an area of the map. We can select a trajectory to extract the depth cut. We can extract the time frequency graph at a location. We can extract also a 3D-dimensional time frequency risk or quantile at a location, and select a single value at a location. For our use case right now, we'll start by searching the map. So to search a map, we have to click on the search panel and enter the parameters. Once the search panel is open, we select the actual parameters that we defined earlier. So central secretary, 2013, annual, frequency at 20 Hertz, and that. So we have selected the parameters, and we see that the map corresponding to these have actually loaded. Next, we would like to see the area of interest, which would represent 32% maximum probability. So let's use the scale here to answer this part. We open the scale, and then we have to select the actual range. So we double click on this one, and then the range will, we'll select the range. So once it's selected, we see that the area is much smaller, and it's easier to see. So actually, we could consider the question answers, but we'll look at some stats on the area. So we'll select the statistic tool, and then draw an area around the zone of interest. So once it's selected, the chart will automatically load, and we see some actual statistics on this specific area. So that would conclude the answer to our previous question, but I will show you some actual use of some of the tools I specified. So for the depth cut, we just have to select a trajectory, and then we'll get the depth cut with the bathymetry, and you can explore what are the actual values on the trajectory. Next, for the time frequency, you might be interested in the frequency at a location. So you can load the actual time frequency chart. Next, we have some 3D cube, which are located at actual buoys that we use to take some measure. And let's select one. So we see the actual cube, and we can use the scale to threshold what we see there. Let's take a monthly time scale. So we see through the year how it looks like. Yeah, so that's quite useful. And then you can select some actual specific values, which you see at the bottom of the screen, the values. So yeah, I think that would conclude most of the utilities. So let's go back to the presentation. Oh, that was it. So thanks to everyone who participate in the effort to make it happen. And the application is available at soundscapeatlas.ucar.ca. So yeah, that's it.
Thanks, Patrice. Thanks for this little tour, this demo of the Ocean Soundscape Atlas app. We have lots of time now for if there are any questions for Patrice about the app. You can ask them by just unmuting your mic, or you can type them in the chat.
Hi, Oliver. It's Bruce here.
Hi, Bruce.
Hey. Really interesting presentations these have been. The guys are doing some really nice modeling and really nice presentation stuff. You know, obviously there's lots of other parts of the world than the St. Lawrence, and the question comes, you know, is there a path similar to what's being done with Kadlu, where this stuff will become available for other people to try and install and run for our own projects, or is it going to be, is the code behind it going to be kept? It's probably so complex you can't think about, you know, releasing it, but it would be fantastic if it could be.
You're talking about Kadlu or?
No, about all the stuff you guys are doing. It's fantastic code, and the ability to look at those depth tracks and the soundscape cubes and that kind of stuff. You know, is that software going to be made available, and the spec for how to put data into the format in the first place?
It has been talked a little bit, but we haven't decided if it would be the actual platform code would be available. But I think there's the scientific part is at the moment. Maybe Pierre could jump in to see if it's the case.
Well, actually, it's not really the case. It's not openly available, but we share it with collaborators usually. But I think also the question is how other scientists can have their data on the website. I think that we were thinking about receiving data from other people, and not just for the St. Lawrence, but let's say for the West Coast or and at some point any parts of the world. But, yeah.
Okay. Yeah, that was about part things. Yeah, actually, yeah, with we talk about the possibility to host some of other research team data for other regions available outside the Atlantic. So, is that something that would be of interest, or you're more interested into the actual platform code, which is quite huge?
That's what I was afraid of. Yeah, I think either one would be of interest. It's the question of, you know, how do we take advantage of all the work you guys have done so that people don't have to redo it in the future if they want to do similar things. But I know it's a tough question. I was just wondering if that's part of what you guys are thinking of or not.
I'm not sure. I think we have to. We haven't really developed our. How could I say it? We haven't really asked ourselves this specific question about the code base. If we would like to have outside collaborators,
okay.
It's possible, but as I said, we haven't really questioned ourselves about this specific scenario. But for the scenario which we could collaborate for the dataset, meaning that if you want to represent another region in our platform, that could be on the table at the moment.
Okay.
But collaborative effort for the code base is it's not something that we do now, but it's not out of the table either.
Cool. Thanks.
Bruce, thanks for this is this was a really relevant and good question. Just adding to what's already been said, it's helpful also to distinguish here between the different parts of the code that's making this possible. On one hand, the very scientific code that produces the model data that then is visualized. So that's kind of one part of the package. And then the other, and I think you made that distinction as well, Bruce, but I just wanted to make it clear for everyone that, and then there's everything that goes into the app itself. The code behind generating the model data, this is code that was developed outside the scope of Meridian. It was developed by the group in Rimouski, and so that kind of has to be treated separately. And then yeah, as Patrice and Pierre were saying, it's something we haven't quite figured out yet, I guess, but it's something that we'll be looking at, how the app part, like how can we maximize the use of that for the community. Okay, I don't. There are no questions in the chat, and I think we can wrap up the first part now. So we're a little ahead of schedule. Hopefully everyone is back from this little break. We're going to have now Matthew Smith from the Meridian team at Dalhousie University tell us a little bit about the intricacies of AIS data management. As we heard before the break, AIS data, so vessel tracking data, is an important component of the Ocean Soundscape Atlas, in that this is the kind of data we use to that is used to track the ships and to model the noise that the shipping creates. And so now Matthew will tell us a little bit about what this data looks like and how to work with it.
Thanks for the introduction. So I'm going to be talking about AIS data, which is vessel tracking data. The intended audience of this presentation is probably people who are considering using AIS data in their research or their study, but have never used AIS data before. There may be something of interest for those who are already using AIS data, but maybe a bit less. So here we go. What is AIS data? So AIS stands for Automatic Identification Systems. This is radio frequency communications that are transmitted by seafaring vessels. It would broadcast information such as position, direction, and speed. The primary use cases for AIS is collision avoidance for vessels in various waterways, traffic management, search and rescue operations, stuff like that. But there's also some interesting research applications, as we just saw from the previous presentation. Some of these might be like investigating vessel strikes, informing policy decisions for marine safety, traffic, and conservation, or tracking the spread of invasive species within Canadian waters. One good example of a study that uses AIS data is a nice paper from William D. Halliday, Stephen Inslee, Casey Hilliard, and Tyler DeJong and Matthew Pine. And they're doing potential impacts of shipping noise on marine mammals in the Western Canadian Arctic. So one thing they noted is that there's an urgent need to assess impacts of shipping in the Arctic before major increases in noise levels occur. DFO lists noise as the greatest threat to bowhead whales, and this would necessitate lower vessel speeds and alternate shipping routes possibly to mitigate that threat. And currently there's no legislation in place for this kind of stuff. So in their study, they're able to use AIS tracks coupled with hydrophone data to assess the Arctic noise. From this data, they could determine acoustic models showing the mean propagation distances based on the observations. And then areas where sound exceeds levels known to influence mammal behavior can be mapped, as shown in their nice info graphic here. So where does the AIS data come from? We get our AIS data originally from Exact Earth. This is collected by their networks of terrestrial and satellite receivers. And then this is aggregated into a Postgres SQL database, which was first built by Casey Hilliard. Occasionally, some of the messages get lost or corrupted in transmission. So what we end up in our database is just the messages that were received by Exact Earth's receivers. Some stats on our database. We have the Neopar satellite database, which is about 7 terabytes of raw SQL, and then another 1.3 terabytes of indexes and other metadata. And this contains global AIS detections from 2011 up until about a month ago. And then we also have a terrestrial data set, which just contains detections from ground-based receivers that are positioned on the Atlantic coast. And our database model uses the PostGIS spatial processing library for querying within spatial boundaries. So here's a quick visualization of what AIS data might look like in the Gulf of St. Lawrence. This would be passenger vessels observed within the month of May. There's a few different types of AIS messages that are transmitted by these vessels and then picked up by the receivers. Each AIS device would have both transmitter and receiver capability. So the Class A AIS devices would broadcast messages about every 2 to 10 seconds while underway or every 3 minutes while at anchor. And these are transmitted at 12.5 watts, so they're better suited for long-range transmission. And the Class A message types that I'm going to talk about include messages 1, 2, 3, 5, and 27. And then we also have the Class B. And this is a bit of a lower priority than the Class A messages, so this will await an available time slot to broadcast. And the Class B contains both self-organizing and carrier-sense subclass messages. And these are only transmitted at 2 watts, so it's better suited for short-range transmissions, about 10 to 16 kilometers. And I'm going to talk about the message types 18, 19, and 24. So here's just a screenshot from my terminal window of the Class A message types 1, 2, and 3. This generally contains voyage info. For example, the MMSI, MMZ, this is the unique ship identifier. We have some other fields here, such as the error flag and line number. This is probably mostly used by the other AIS devices. We have a timestamp, the region, the length of the data, navigational status, the rate of turn of the ship, the speed over ground. This is measured in knots, and the course over ground, so the direction that the vessel is traveling in. General voyage information, stuff like that. The message 5 data essentially contains a bit more additional voyage info. So we have a few other fields here, such as the ship type. In this particular example, we have a ship type of 30, which would describe a fishing vessel. We can also see that we have the dimensions of the ship here. as well as the drought, the destination, and some AIS metadata, as well as the estimated time of arrival to the destination. Message 27 is basically a compressed version of messages 1, 2, 3. So it's more suitable for long-range detections. In this one, there's no timestamp actually transmitted within the message. The timestamp is recorded by the receiver. We also have an additional column here, the AIS geometry, and this is generated during the pre-processing, the loading into the database step. And this is used for spatial queries using the PostGIS extension in our database. The class B message 18 and 19. So this contains some AIS device metadata. For example, the unit flag would describe if the AIS device is self-organizing or if it's a carrier sense type device. And so this is a screenshot of the message 18, and the message 19 is essentially a more detailed version of 18 used by certain devices. For the message 24, this also contains some ship metadata. This is commonly used to associate a vessel identifier with a vessel name. For example, in this one, you can see the timestamp, the call sign. There's no vessel name for this particular message. Sometimes you have data where data is missing. And these are transmitted at least once every 16 minutes or 6 minutes. So that's pretty much all of my presentation. I'd like to thank Oliver Kirsebom for helping me proofread this and for the nice introduction, as well as Casey Hilliard for answering all of my AIS questions. So here's some of the references I used. And as a final note, if there's will this AIS data benefit your research? For any access and inquiries, you can visit our website, or as well as email me directly. So now's a good time for questions if there are any.
Thanks, Matt. Yeah, the floor is open for questions to Matt. Again, either just by unmuting your microphone or by typing in your question in the chat. I can just add or elaborate a little bit on the last thing that you mentioned there, Matt, is that MERIDIAN, through our partnership with exactEarth, we can provide AIS data. We have a number of licenses, maybe 12 or something. And so if you're interested in making use of AIS data for a research project, then get in touch with Matt and myself, and we can have a chat about that.
I see there's one question. Is there an effort to quality control the data? I believe that exactEarth does some quality control, as well as a quality control done in the loading into the database step. So I know Casey, who built the database, put a lot of effort into doing quality control when the data is loaded into the database. So yes, there is some quality control there, and as well as removing spurious reports during the extraction phase.
I could add that so Matt has been working on this since only since July this year. Casey Hilliard, who was our AIS expert for many years, he left MERIDIAN to take on a job in industry earlier this year. So Matt is still sort of in the process of figuring out the entire pipeline here. Okay. There's another question there, Matt. Do you see it? It's Bill asking about the end of the AIS coverage. So I guess, Bill, your question refers to sort of the timeline, given that Meridian is that we're well, we're not funded forever, I guess. So is that what your question is about? Yeah. Okay. Yeah. So my understand. Well. Okay. Yeah. So that's a good question, actually. Originally, the project was set to end this year, right? But we've been extended by CFI for another year, so till the end of next year. I haven't been in touch with Exact Earth to sort of confirm that that means the licenses are still valid for another year. That's probably something I should do. So thanks for asking that question. So I would assume this would still work at least for the next year, but it's something I need to look into. Okay, and Matt, I don't know if you saw it, there was a comment from Ivan who posed the previous question about the quality control, that AIS fields are sometimes or even often wrong. And so thanks for that observation, Ivan. I think that's something yeah, we'll look into after this webinar. It'd be interesting to, if you could share with us some of your experiences in regards to working with AIS data, and especially the types of errors that are most often found in these data. And then we can have a look at our end, at our data processing pipeline, to see to which extent we're already handling those errors, and perhaps there may be places in which we can improve the quality control that we're already doing.
Okay, yeah, thanks for listening, everyone.
Thanks, Matt. Okay, that means we're now at my presentation. So let me just try to share my screen here. There. Okay, so this today's fourth and final presentation is about the open source Python package that that's called Kadlu, and this has been is a package that's still under development by the Meridian team. So this is an effort led by myself and Matt, and with support from David Barkley, who's an oceanographer at the Department of Oceanography at Dalhousie University here in Halifax. So as we heard earlier today from Pierre, it's customary when we speak about underwater soundscapes to consider three different types of sources of sound and noise. The first one being the anthropophony, so the man-made noise. And then we have the biophony, sounds produced by fish and marine mammals. And finally, the geophony, which is the noise that's produced by earthquakes, waves, rain, thermal agitation of the water molecules, etc. And so in this project, the motivation for starting this project was really that that we wanted to produce some modeled maps of the geophony in the St. Lawrence to contribute to the Ocean Soundscape Atlas that we heard about earlier today. Now, looking at the ambient noise levels in the ocean, it's useful to consider this as a function of frequency, which is what you see mapped out here in this figure on the left. And there's a lot going on in this figure, but what I'd just like to highlight is that essentially it's the curves in blue labeled 642.1.5. So these are showing the noise created by, in the caption, what it's called wind-dependent bubble and spray noise. So this is essentially the action of waves, largely driven by wind, which is producing noise. And then depending on how big the waves are, the noise will be higher or lower. But what you notice is that going above 100 hertz or so, the ambient noise level in the ocean will often be dominated by noise from waves and rain. And so that's why it's relevant to be able to model this contribution to the soundscape so that we can determine when, say, shipping noise exceeds this already existing ambient noise level. So just a quick glance at Kadlu. I'll have more details for you just in a moment. So Kadlu is an open source Python package that provides tools that are supposed to make it easier for researchers to perform ocean ambient noise modeling. So some of the main features brought to users by Kadlu is automated fetching and interpolation of environmental data. And I'll elaborate a little bit on that in just a moment. Accurate numerical treatment of the sound propagation and calculation of transmission loss. And finally, a step that we're still working on, which is to have the model output saved to a structured database along with relevant metadata. So starting from the left, you see this box here with various environmental data sources. In order to perform the modeling, we need to bring in various types of environmental data. This was something that Pierre also discussed in his presentation earlier today. So we need to have data, and this will typically be modeled data that we're going to use here, but we need data on temperature and salinity to build the sound speed profile. We need data on the bathymetry, so the depth of the ocean floor. And we also need some data on what the seafloor is made of, seafloor lithology, to be able to accurately treat the reflection of sound waves on the ocean bottom. And then in addition to this, because we want to model the geophony, we also need to know about waves, winds, currents, and tides, and really any variable that's correlated with noise production in the ocean. So what Kadlu provides is routines for automatically fetching these data from online repositories, some of the major online repositories that provide modeled ocean data. This is then downloaded, given a selection of a geographic region and a time period. These data will be downloaded and saved to a local database wherever you're running Kadlu in an SQLite database. And then we have a module that handles the sound propagation modeling, so the calculation of the transmission loss. And then the user can play with different parameterizations of the source levels, and combining that then gives you your map of sound pressure levels, which would then finally be outputted to a database file. Just a few details on the sound propagation model. So I've included here to the right the same table that Pierre showed us earlier today, which gives you an overview of the different types of models that one can, or mathematical treatments that one can use for performing for calculating transmission losses. As Pierre mentioned, they have each their strengths and weaknesses. The approach that we've implemented at this point in Kadlu is the parabolic equation approach, which has the advantage of being able to handle range dependence and works very well in shallow waters for low frequencies. And so this has been implemented purely in Python using a split step Fourier algorithm on a regularly spaced grid. In terms of the data sources that we're using at the moment, they're listed here in this table. So we use the ERA5 database extensively to source data on wind speeds, wind direction, wave height, direction and period, also precipitation data. And then we use the HICOM repository for salinity and temperature and ocean currents. And then as an alternative to ERA5, we also have set up automated fetching of data from the WaveWatch 3 repository that's maintained by NOAA. And finally, we have GEPCO as our main source for bathymetry data. And then as we progress with this project, as we identify new useful data sources, we try to add these to the to Kadlu. A little bit about the software package itself. So as I've mentioned already, it's written in Python and it's open source under a GPL license, which essentially means it's freely available to use and modify. It's hosted on GitLab, which is a great platform environment for collaborative coding. And the code is fully documented. We try to include examples for at least the most important functions and methods. And then we also have step-by-step comprehensive tutorials, which I think is a great point to get started with using the software package. The software package is available through the Python package index, which is the official third-party software repository for Python. Now, if you're wondering about the name of the package, Kadlu, then, well, it comes from Inuit mythology. So apparently Kadlu refers to one of the Trinity sisters, which are 3 goddesses for creating thundery weather. And Kadlu in particular creates thunder by jumping on hollow ice. So we thought that was related to what Kadlu is trying to do here, which is to model underwater noise. Kadlu relies on a number of well-known and widely used open source Python packages. So for much of the numerical work and for the data interpolation, we rely on SciPy, NumPy, and Pandas, and also the GSW Python package, which is the Python implementation of the thermodynamic equation of state from, I think, 2010. We then use SQLite and NetCDF as 2 database formats. And finally, for data visualization, which we have a bit of in Kadlu as well, we use Matplotlib and Cartopy. So as I mentioned, we have extensive documentation on this package, and hopefully this will facilitate use and encourage use of this package. And you can find the documentation at this URL that's at the top of this slide. And I think of most interest probably to you will be the tutorials. I think this is the best place really to start if you want to try out these the functionalities that Kadlu provides. All right, so this brings me to the summary of this short talk. So Kadlu is an open source Python package for ocean ambient noise modeling. Its main features, as I've mentioned, is automated fetching and interpolation of environmental data, accurate numerical treatment of sound propagation, and then the part that we're working on right now is to have the model output saved to structured NetCDF database format, including relevant metadata. And I encourage you or welcome you to check out the software package at the URL that you see here. Okay, yeah, so that's the end of my presentation. I will stop sharing screen here. So if there are any questions to this presentation, either unmute your mic or just type them into the chat, and I'll do my best to answer. I don't see any questions in the chat, so I think we can move on, and that actually means move on to wrapping up today's webinar event. Let me just bring up a final couple of slides. There. So yeah, so I think just to wrap up here at the end, I'd like to thank you all for attending. I'd like to thank you for your support and interest in the MERIDIAN project. You see here, if you'd like to get in touch with us, you can go to our website or you can email us at meridian@dal.ca. Also, I'd just like to advertise that we have a number of webinars coming up in the near future. This is the first of 7 webinars that will showcase many of the software tools that MERIDIAN has been working on in the last couple of years. So in a week from now, we will have a webinar about fish sounds. A week after that, we will have a webinar about a group decision-making tool. And then in December and January, we have a couple of webinars that focus on various aspects of acoustic detection and classification algorithms. And then finally, in January, towards the end of January, we will have a webinar focused on acoustic data management and a webinar dedicated to a new Python toolkit for acoustic tracking data analysis. And if you're interested in attending any of these webinars, you should be able to find the Eventbrite pages for these webinars from the Eventbrite page for today's webinar. Okay, with that, I think I'll bring this webinar to an end. We're a little bit ahead of time, but I'm sure no one has a problem with that. So thanks again for joining, and hope to see some of you next week for our webinar about fish sounds.